Okay, so get everything in order. So we last left off talking about voltaic cells, the idea that by combining these oxidation and reduction reactions together, they're going to produce some electricity that we can pull out. Now, just like acids and bases, strong acids will react with weak bases, and the strength of the acid is going to depend on which one actually reacts. Same thing with our dear half reactions. The stronger one for oxidation is going to react with the weaker one for reduction, and we're going to always try to create the largest voltage in the positive direction. So we mentioned anode. Anode is the oxidation, cathode is the reduction. And as we write these guys, look at them, it's always going to be anode first, followed by the cathode. Anode always followed by the cathode. So, okay. So this is just a pictorial example of a simple voltaic cell. Of course, it doesn't look like this at all if you want to get into an actual battery, but the same general premise is there. In that we have a solution of some sort for both anode electrode and cathode electrode, some wire connecting them, and some salt bridge that allows the liquids to mix. Now, if the two liquids were together, then you might not need a salt bridge. But you also have to make sure to keep the solution from shorting itself out by reacting until death. Okay, so there's a shorthand notation to write those cells without having to draw out a picture each time. And we're going to use these two little barriers. In the shorthand, there's going to be a single straight line and a double straight line. And those are going to be showing the single straight line is going to be used to indicate a separation of electrode from solution. Now, the double straight line are going to be used to indicate a separation from anode and cathode. But the way we're going to use this is we're going to be able to write exactly what's going on here just by using these things. So we'll write, it's going to include all components, the electrodes, everything except the salt bridge. It's going to include the concentrations and everything. And it's always going to be anode first. So that picture in the last diagram saying a zinc electrode dipped into a 1 molar zinc solution is the anode. The cathode then is made up of 1 molar copper with a copper electrode dipped in there. One way to look at this is essentially this here's one beaker, there's the other beaker, and we got our salt bridge connecting the two. But here's our two solutions, and this is the electrode that's being dipped into there. But it's just a shorthand way of quickly writing out what exactly is going on in a voltaic cell, saying that zinc, and you can read it from left to right. Zinc is being dissolved to go to zinc 2 plus. Copper 2 plus is being precipitated as copper solid. So I'm reading from left to right. This guy's going to there. This guy's going to here. That's one of the advantages of writing anode first. It can proceed in an orderly direction, showing which way the chemistry is occurring. Now, we're not always going to have the a solid going to a solution. we might have a situation where a solution is just being partially oxidized, or we're going to a gas, so we're not forming a metal component. So what if we're going from iron 2 plus to iron 3 plus? Both of these are aqueous, so we may not have a solid electrode. What if we're going from hydronium to hydrogen gas? You're not going to have an electrode right there we're not going to be able to put hydrogen gas and form it as a solid and use it as a electrode. So in that case, we're going to use a non-reactive conducting electrode. Most of the time, that's platinum. Platinum is really expensive if you don't already know that. One of the reasons platinum is very expensive is because it is very, very non-reactive. It conducts electricity very well, but it's not going to undergo these chemical reactions. It has too high of a potential to be oxidized, so you don't have to worry about this degrading over time. So you can keep using this again and again. You might have to clean it off, for example, if you're precipitating a solid onto it, but it should stay with it. So for example, if I put fluorine gas and 2 iron 2 pluses goes to 2 iron 3 pluses and fluorine minus. Fluorine is being reduced, iron is being oxidized. So this half reaction looks like, so platinum, there's our electrode. Now in solution, we have 1 iron 2 plus going to 1 molar iron 3 plus. So these are both in the solution phase, but still going left to right, iron is being oxidized. Now, the other half reaction, fluorine is being reduced. That's F2 gas, 1 atmosphere, being bubbled into solution, and it's forming 1 molar F minus, aqueous, also with a platinum electrode, because none of these are solids. If you form a solid, obviously you can use that as your electrode. But if you're not forming a solid, you need a non-reactive electrode like platinum. So still written, so the reaction is going left to right, left to right. So this guy is going to that. This guy is going to that. But this is just telling us literally what this cell would look like. If you can picture this, if you're a good visual learner, you can picture this, what this is actually going to look like. Now, some people don't have a good ability to picture it, and we can work on that. But this is just a shorthand notation. So, like on a test, I could write this, you know what's going on, and not have to, I don't have to have like attached image. So, okay. Here is first clicker question of the day. We have a lot of people. Once again. Wow, we have 22 people. Once again, if you do not get, if your clicker is not working, send me an email. Send me your answer. So take your time. Identify the cathode on that reaction. Which one is the cathode? Remember, we think of the cathode as the electrode, not as a reactant or a product. We think of cathode and anode as the electrodes. So that already may have knocked 2 of your answers down. Take your time. I expect to hear some buzzing from my phone as I get some emails. Take a hot minute. Give you to like the 2-minute mark, maybe 2:30. Just make sure. Okay. Uh, I'll go ahead and stop it in just a second. So still waiting. Put in a guess. Put in a guess. Put in a guess. 5, 4, 3, 2, 1. Okay. So cathode. Cathode is where the reduction occurs. So electrons flee from the anode to the cathode, meaning that would be the solid copper. Solid copper. So the electrodes are where the action's at. That zinc would be the anode. Copper is our cathode. Okay. Now, how do we calculate the standard cell potential of these? It's all well and good to be able to draw these and understand these, but what values are we going to be calculating? So the work done by a voltaic cell is known as the electromotive force, or EMF. Now we measure this work as a cell potential, which we're going to call the E cell. So the electromotive force for that cell. And we're going to measure that in units of volts. Now, what is a volt? A volt is defined as a joule, which hopefully you remember what a joule is, that energy we talk about with heat. But a volt is a joule divided by a coulomb. A coulomb is our electronic charge. Like when we measure the charge of an electron, it's measured in coulombs. So we're measuring how many joules are being transferred per coulomb of electron. So it's a way to quantify this in terms of electrons, kind of like a speed. Now we can calculate the cell potential at standard and non-standard conditions the same way as we calculated delta G at standard and non-standard conditions. But either way, to calculate the E cell of a redox reaction, we will simply subtract the individual cell potentials from each half reaction. Specifically, we will subtract the reduction potential from the oxidation potential. So the reduction potential of the cathode, cathode minus anode. Now, since there is no such thing as an absolute reduction potential, we will artificially set a reference point as 0. We cannot measure one half reaction by itself. It's just physically impossible because whenever you have an oxidation, you have to have a reduction. You have an oxidation, you have to have a reduction. So we've artificially said, oh, hydrogen is going to going to hydrogen gas. That seems like a pretty good 0 point. And we say, oh, okay, so we're going to put that in the middle, put that as 0, and everything above that is going to be positive. Everything below that's going to be negative. The same way with delta G, we said, oh, the formation of solids, the pure elemental solids, we said those were 0. Same thing with delta H. We didn't have an absolute value, but we found a way to calculate everything from an artificial absolute. So we set this as 0 and measured everything off of this standard hydrogen electrode. And so by measuring that, we got all the values. Now you'll notice it says E naught reduction of the cathode minus E naught reduction of the anode. So the table we're going to see in a slide or two is going to give you all the reduction potentials for every reaction, every little half reaction. Now, what we're doing is, if just like with an acid base, if it's a strong oxidant, it is a weak reductant. But a strong reductant, it's a weak oxidant. Just the same way with a strong acid, it's a weak base. So if we measure all of them in one way, we can we know all of the other answers just fine. And so we're taking one guy which reads as written and subtracting the guy that reads opposite from what we expect. And so it's going to make things a lot easier. We don't have to do crazy math. We just have to look, see where the reactions show up identical and not. So here's an example of a standard reduction potential table. Try to remember if this is the one in your book or if this is one in another book. But this is how it looks like. In this particular table, they give them all in numerical order. So this is not alphabetical order. This is by cell reactions. 2.87 is the largest and moving down. It's dropping, 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 dropping until we get to, there's our hydrogen, and then it drops into the negative. But notice each of these reactions are a reduction. F2 plus 2 electrons goes to F minus. Cerium 4 plus 1 electron goes to cerium 3. Nitrate plus 4 hydrogens plus 3 electrons goes to nitrogen monoxide and 2 waters. All these happen to be balanced for all the oxygens and hydrogens. There's oxygen being reduced to hydrogen peroxide. There's copper being reduced to copper solid. And that all these guys are reductions, even if they don't want to be reductions. Lithium, 1 electron goes to lithium solid. All these values are given as a reduction for our convenience. So the position on the table shows the likelihood of being reduced by or reducing hydrogen. So everything above hydrogen are going to be reduced by hydrogen. Everything below the table, below hydrogen on this table, are going to reduce hydrogen. So the guy who's on the higher up on the table is going to react as written. The guy lower on the table are going to react opposite as written. Now here's a big thing. When we dealt with delta G, we had to calculate the moles of each reactant and to factor that when we calculated our delta G and our delta S. When we do this, because it's joules per coulomb, it doesn't matter. We don't have to balance the chemical equation. We just have to mix them together. Joules per coulomb. So that this calculating this, it's 1.99 calculates it for 1 electron. This 2.87 is calculating it for 2 electrons. So it's already factored in that there's 2 electrons in there. So we don't have to use the coefficients. So using this, 2 gold, 3 plus, and 3 hydrogen 2 goes to 2 gold and 6 hydrogen. So I'm going to look, where's gold 3? Gold 3 right here. Gold 3 plus 3 electrons goes to gold. Reads 1.5. Doesn't matter that there's 2 and 2, we still use 1.5. 3 and 6, well, it's 0 anyways, so even if we had to multiply by 2 or multiply by 3, it would still give you 0, but we don't even have to do that. So notice, this one is not 2H plus goes to H2, it's H2 goes to H plus. This is opposite of how we see it on this table. Because this is opposite, we subtract. We subtract. So 1.5 minus 0, well, it's still 1.5. But it's as written, which is our reduction, minus opposite, which is our oxidation. So the cell potential for the reduction of gold with hydrogen gas would be 1.5 volts. Now, as we're going to see in a little bit later, this would be a spontaneous reaction.
How does that work?
It's going to be this, what work?
Well, like I don't I just don't understand that.
The next slide we're going to do some practice.
Oh, okay.
Okay, so So let's look at this. So let's measure the cell potential for these guys. So move this up so we can out of the way. So we're gonna look, where do we see cobalt 3 plus? Cobalt 3 plus is right there, which has a cell potential of 1.82. And silver solid and silver plus 1. Silver solid and silver plus 1 is right there. So looking here, which one of these reactions perfectly matches the order as we see it on this reaction? Was it cobalt or silver? Which one has
Cobalt.
Cobalt? So we're going to say 1.82. So that means silver is opposite. You see silver plus, silver solid. You see silver solid goes to silver plus. So we're going to take that number and subtract it. So the opposite gets subtracted. So what is the cell potential for this first reaction? 1.8 minus 0.8 is give us 1.02.
What I can do is I can send you all of my cardiac or all my critical care notes from Blue Vitals.
You may want to mute yourself.
Okay.
But yeah, it's not as bad. I heard a story about someone had a bird fly into a kid's classroom and
when you're CDP,
go into a kid's room and like set everyone off.
Oh no, they do nothing.
Chlorine, chloride. Well, that one's pretty easy. Chlorine, chloride, that's 1.36. And we have, this one's a little bit hard. Hydroxide, oxygen, and water. So there's oxygen, acid, and water. Let's keep looking. That's not exactly what we want. There's oxygen, hydrogen, and peroxide. Nope, still not there. Oh, there we go. Oxygen, hydrogen, and hydroxide. So right there. So some of these guys have a different cell potential in acidic versus basic conditions. Under acidic conditions, this was 1.23 volts. Under basic conditions, this is 0.4 volts. So a big change. Once again, chlorine, chloride, that matches that guy. So I'm going to use 1.36 as our reduction minus our oxidation. So hydroxide, hydroxide, oxygen, and water. So I'm going to minus 0.4. This is going to be, well, 0.94. Wait, no, sorry, 9.96. Got to do my math good. 0.96. So I'm going to finish this problem, and then we'll switch over to the second video. Okay, so copper. So copper, let's look for copper. Copper is Cu. There we go. Copper plus goes to copper. That's, hopefully you'll see. If it matches this point, we use it. If it opposite, we subtract it. Now here's a tough one. We want to do the most spontaneous reaction. We want to do the most spontaneous reaction. But the key thing to always keep in mind, when you're doing a problem, do the reaction that's written, not the one you want to do, not the one that gives you the biggest number. Do the reaction that's written. If it just says, look at this half reaction and what is the cell potential, it will always be spontaneous. But if they give you a written reaction, you must always do it as written. Even though this is a negative cell potential, and that's going to be a non-spontaneous reaction, as we're going to see. This can still happen if you're putting electricity into it. If you're putting energy into it, you can make this happen. Now, is it going to happen by itself? No. but it can happen. So if you're given a chemical reaction, always use it as written. So don't cheat and just say big minus small. You want to always do the reaction as written. Last one, and then we'll stop. H2O2 goes to, and H2O2 goes to H2O, and what? H2O2 and H2O goes to H plus. Sure. Actually, this one's a little bit harder. Let's find the chromium first. Chromium goes to dichromate. Mm-hmm. 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 I'm not finding that dichromate anywhere. Where?
It's right under the.
Okay, I cross that out. Okay. Right. Here's the problem. So here's the problem here, in that you notice this has 14 hydrogens and that has 8 hydrogens. When I added these guys together, I crossed off some on both sides. So when I balanced this guy, I lost some of my reagents. But the fact that there's 8 plus, so there's probably the peroxide and acid. But peroxide had to go to water. So let's look at our peroxides. So no, not that. There's only so many peroxides. I'm just trying to figure out which one it is. We don't have any oxygen, so it's not that guy. Oh, it's this guy.
Yeah.
There. The peroxide is 1.78. I'd love to spend the time to try to balance this out for you, but 1.78 and 1.33. This is the hardest thing I could possibly give you, and I'm not actually going to probably give you that on any sort of test. But that'd be what? The answer is going to be what? 0.045. Let's look at that. So 3 peroxide. So 3 times that. So 3 peroxide plus 6H plus goes to 6 waters. And the other guy, dichromate, so Cr2O7, 14 hydrogens, 7 waters, and 2 chromiums. Cross all but one out, cross all of those out. Cross all of those out, cross all but 8 out. And there we have our balanced equation. So after we balanced this guy, we lost a lot of the information there. So that's the hardest thing you could possibly ever see, in that where it like didn't directly you didn't see all the reagents. So well, we'll do this clicker question just so that we don't have a bunch of people coming in to that clicker, to like a clicker question and missing it. So we'll finish this. This will be the end of this little video segment, and I'll start the next one in a minute. So identify the spontaneous cell. So literally, remember, the guy on the left is the oxidation. The guy on the right is the reduction. So, and the cell potential is reduction minus oxidation. So which one of these guys would give you a positive number? Which one of these guys would give you a positive number? There's a trick to it. One of these guys is not like the other. Give you another 30 seconds. So. To 2:30. 2 means 30 seconds. Okay, and okay, so if the guy on the right is the reduction and the guy on the left is your oxidation, you're going to take whatever number you get from this side minus whatever number you get on this side. So the best way to get the largest number is to subtract a negative. We do not want to add a negative, we want to subtract a negative. So with that in mind, copper, which would be 0.52, minus negative 0.44 would give us 0.96. If I did this one would be negative 0.44 minus 0.52, that gives us negative 0.96. This guy, negative a lot, negative 2 something, 2.18. This guy, even though you're minusing a negative, this guy is much bigger negative. Negative 1.66 minus a negative 0.44 gives us negative 1.22. The best answer is D. Okay, so stop this. Come on. Okay, there we go. So here's where we start to loop things back into the last chapter. We're going to build on what we learned in the last chapter. We kept on referring to a spontaneous cell. Spontaneous cell. So how do we relate a free energy cell to a reduction potential? And so it has to do with the sign and magnitude of the cell potential. We'll tell us about the spontaneity. So we actually have a reaction that says delta G standard equals negative N F E cell. So Faraday, yeah, that where we know delta G, we know what E cell is, at least hopefully. N is the number of electrons transferred. N is the number of electrons transferred. And F is a constant known as Faraday's constant, which is 96485 coulombs per mole or 96485 joules per volt mole. But it's a Faraday's constant named after Michael Faraday. What this is going to allow us to do, if E cell is in volts, this is going to get our volts into joules per mole of electron. Then N is going to get us into moles of electron per mole of reaction. So, while E cell did not matter how many electrons were transferred. E cell did not matter how many electrons were transferred. Delta G does. And so we have to use the total moles of electrons to calculate that. So if there's 2 moles of electrons, it's 2. If it's 5, it's 5. The greatest common factor is 10, we have 10. But delta G equals negative NFE. So this is a constant. This is something we calculate. This is something we look from the chemical reaction. So if this was a positive number, this negative sign is going to give us a spontaneous delta G, which is our negative delta G. If this was a negative number, that's going to give a positive delta G, meaning it's non-spontaneous. So just looking at that. Now Faraday's constant, it's not just a magic number. It is calculated by looking at the charge of electron, which is a constant that we learned in chapter 2, times Avogadro's number. So we turn electrons into moles of electrons. So we get coulombs per mole. Just a way to scale up the insignificant charge of electron into something we can actually start looking at. So just an example of this in action. Nickel goes to 2 silver plus, and 2 silver plus goes to nickel 2 plus and silver solid. Now in this goes, each silver is gaining 1 electron, but there's a total amount of 2 electrons gained. Nickel, each 1 nickel goes to nickel 2 plus, meaning there's 2 electrons lost. So the total amount of electron transfer is 2. You could calculate the E cell of this as 1.08. So how would you calculate this? It's negative 2 times a constant times 1.08. It's going to give you a very big number, but that's going to be a big number in joules. So you turn that joules into kilojoules, and it's going to be still a big number. Negative 208 kilojoules is still very spontaneous. So most of these half reactions will go like a shot. They will go by themselves if you give them the opportunity to go. That's why iron rusts by itself, as long as you have the proper conditions. You need oxygen, you need the water, but it will rust because most of these reactions will be very spontaneous. Now we can also relate this to equilibrium because the fact we knew delta G and related it to equilibrium, we can relate E to equilibrium as well. That, remember, delta G equals negative NFE. We just learned that 3 seconds ago. But we also, last chapter, learned delta G equals negative RT ln K. So setting those two equal to each other and dividing by NF, negative NF, we get that that E equals RT over NF times ln K. So temperature could change, but it's usually 298. F is a constant, R is a constant. The only thing that's really going to change is this N, the moles of electrons. The only thing that's really going to change is N. That's going to relate. What?
You have to look at the charges to know about your electrons, correct?
Yeah, you have to look at the balanced chemical reaction to look at your electrons. Yes.
Okay.
Now, so that means if E is positive, K is going to be positive and going to be very product favored. So a lot of these guys, if you try to calculate your K, it's going to be ridiculously huge. Might even break your thing. So this guy, looking at that, we said 2 electrons transferred there, 2 electrons transferred there. They don't add up to 4. 2 electrons lost or 2 electrons gained. We're just looking at how many total electrons are transferred from left to right. So looking at this reaction at 25 degrees, 1.08, 2, 96485, 8.314, 298, natural log K. So what I would do is I would move all those to the other side. So 1.08 times 96485 times 2. divided by 8.314 divided by 298. You do that, you get the answer is 84.11 equals natural log of K. Now, how do you get 84.11 into K? You're going to take the inverse natural log. So e to the factor of 84.11 gives you this answer. I rounded it, so I got 3.37, but still pretty close. 3.38, but 3.39 times 10 to the 36th power. So, considering the only part that's going to be part of this chemical equilibrium, remember, the only part that's going to be part of the chemical equilibrium is the nickel aqueous and the silver aqueous. Solids will not count. Your K expression would just literally read this. K equals nickel 2 plus over silver plus squared. So just the idea of that. I'm just looking at it. So let's see. You would have a ridiculously small amount of silver to get that amount. You would have to have like almost no silver present at the end of this reaction in order to get that really, really, really large amount of K. So that should tell you, if you let this reaction go and fully go, it will completely wipe itself out until it's like practically dead. It will eventually slow down and stop, but it takes a while. Batteries are really good. So let's actually calculate these. First, what would be the delta G for this reaction at 25 degrees? Then, what is your equilibrium constant for this reaction? So, reading it as written, so if I put sodium solid into chlorine gas and it forms sodium chloride, what would this go? So chlorine goes to chloride is the reduction. Sodium goes to sodium plus is the oxidation. It is opposite of as written. So I'm minus a negative 2.71. 1.359 minus a negative, which is the same as adding a positive. So our cell potential, E cell, is equal to 4.069. So delta G is equal to negative NF. Our E. Faraday's is a constant. The only question here is how many electrons are transferred. So looking at our balanced chemical equation and looking at these, what is the greatest common factor between this guy and this guy? 1 electron here, 2 electrons here. The greatest common factor is 2. So our delta G is going to be negative 2 times Faraday's 96485 times 4.069, and then we probably want to divide by 1,000 for good measure just to get this into kilojoules. So negative 2 times 96485. You get a crazy large number. -785.19. Holy cow, that is very, very spontaneous. It's very, very spontaneous.
Is it spontaneous in the fact that it's negative?
Yes. What?
Okay.
Negative and big.
Okay.
Negative and big. The bigger the number, the more spontaneous this will be.
Mississippi was talking about letting their kids go back to school and then
So,
said no, cancel all of them.
so it's basically like saying, how much potential energy do you have stored up in there? It's not just, oh, I'm dropping this rock from off of Hall. It's like, no, I'm dropping this rock from off the space station and letting it fall to Earth. It's like, well, that's a lot more buildup of kinetic energy as long as it doesn't reach like the minimum velocity or whatever, the maximum velocity. So let's use that. So I have some room. And the last one. Now, certain textbooks will actually just abbreviate this and give you that, say, E. They'll give you this whole thing as a constant. They'll say, oh, this is equal to some number over n log of k. I don't like to do that. But you should get close to the same answer. One, I don't know why they switched to a log. That never made sense to me because it's not like a log is any easier than a natural log. Because if you know how to do a natural log, you know how to do a log. But so let's start looking at this. So E 4.069 times NF over RT. So 4.069 times 2 times 96485 divided by 8.314 divided by 298. It's going to give you 316.9 equals ln k. Now that's okay if this is where you get stuck, because if you do the natural log of this number, the inverse log of this number, it breaks your calculator. It says error overflow, meaning this is so big a number, it's saying like when you get to times 10 to the 99th, it stops. It cannot calculate this anymore. It says when you get above that number, it just says, nope, I'm done. And it goes home and quits. Now, there's a way to secretly calculate this. I'm not going to bother to teach that because that's just silly. It's like, it's not super useful. In math, maybe, but in us, we're not going to see this too much. But I've actually calculated for the sake of this problem that, well, it's essentially 4.25 times 10 to the 137th. So that last one was very spontaneous. This is incredibly spontaneous. The amount of sodium chloride you would produce is off the charts. That this is, you put this together, this would be explosive amounts of power, explosive amounts of energy. It wants to go to products. You need energy to split this back apart. We can do it. That's how we can make chlorine gas pretty easily, by taking salt water and putting electricity through that, but it takes energy to do that. So, but needless to say, this naturally wants to do this. And naturally, if I put sodium solid into chlorine gas, it will go like the Dickens. Just, and it's just no stopping it.
So is it safe to put like electricity through that?
Oh yeah, you could do electricity. The idea is that if you can separate them, and that sodium forms on one electrode and chlorine forms on another electrode, that you could put electricity through salt and split it, as long as you try to keep it from recombining. So it's just a matter of separating them at their separate electrodes, and then you can get pure sodium. In fact, I think that's probably how they get pure sodium, because sodium is so darn reactive. It's easier to like crystallize it there. I mean, you might be able to. I don't know. It's been a while since I've looked at this, but yeah, you can do that. It's just a matter of keeping them separate, because it's like I'd have to look at the delta H for that. But needless to say, that's going to be pretty high. So we'll do this one practice problem, this last practice problem, and probably call it a day. I don't know if there's a clicker question after this. If there is, we'll go ahead and do that. But if not, we'll call it a day after this problem. Now, based on the Gibbs of the following reaction, what is the E cell? So how about going backwards? This is the Gibbs of iron essentially rusting. The Gibbs of iron rusting. So the delta G, so we said delta, no, I got to annotate. We said delta G equals negative NFE. So the only thing we have to keep in mind is 632.17. Well, first things first, we have to multiply by 1,000 to get kilojoules into joules. Then we're going to divide by negative N and Faraday's constant, which is 9.648. No, 5. Now, the only question you need to know right now is what is the amount of electrons? Now, oxygen might be a pain in the ass to try to figure out the number of electrons transferred. So what's the easiest one to look at? Let's look at iron. This is iron, goes to iron 2+. So each iron is losing 2 electrons. Now, how many ions are losing 2 electrons? Well, 2. So how many electrons are totally lost by all the ions? 4. So our N is 4. Now, if we look, oxygen is going from 0 to 2-. So each oxygen is gaining 2 electrons, so a total of gain of 4. So as long as you can figure out one element, you can figure out the other element. They should be the same. So always do the easiest one. Don't push yourself to try to do everything. But so negative 632.17 times 1,000 divided by 4, or negative 4, divided by 9.6485. You get, what is the cell potential? It's 1.64. So I'm just using my equation in reverse. Use my equation in reverse to work that out. Now this, I'm showing all of the units so that you can see unit cancel, unit cancel, unit cancel, blah, blah, blah. You don't have to worry about that so much, as long as you remember the equation. Okay, yeah, we'll do this clicker question, and then this is where we call it a day. Last clicker question of the day. So when E cell for a cell potential is positive, what must be true about delta G and what must be true about K? So based on the problems we just worked out, if the cell potential is positive, what must be true about delta G and what must be true about K? So got to think about what it means for delta G to be negative versus positive, and what it means for delta K to be large or small, greater than 1 or less than 1. This is where we'll end for today. I wanted to do this so that while it's fresh in many of your minds. Also, it seems like a lot of you joined in a little bit late, so make sure it didn't cheat you out of a chance. So, how we doing? Give you to the 2-minute mark, and then we'll call it a day. Now, this may be all we're getting. Okay. Get those last few ones in, and okay. Yeah. Okay. When delta E is positive, we must have a spontaneous reaction. Spontaneous reaction would have a negative delta G. When a reaction is spontaneous, it is product favored. Product favored K would be a K that is large, which is greater than 1. Oh. So a negative delta G gives a large K. Yep. That's where we will stop today, and we'll pick this up on Wednesday. So have a good day, and keep on working. So this has been the Chemistry Cowboy. Once again, if you like what you see, please like, please subscribe. I'll be posting more videos to give you the education you need. And I've been asked to put this disclaimer to Bethel students. Remember that the log and the online learning guidelines remain in effect while interacting with any type of instructional materials / sessions. That over and out.